G'day mate, it's me, Willie, the Tapwise Owl. Down under, we've got a cheeky little game called 2 Facts and a Fib. Reckon you can spot the porky? Number 1, before hitting record, Andrew swore blind that this was a ripper idea and that my true blue Aussie accent would be a smash hit with all you crafty beer professionals on the YouTubes. Number 2, Tapwise makes it dead easy to run your beer club and bring your mates back to the bar with your very own branded brewery app. Monthly subs are a breeze, perks and rewards tick along on autopilot, and the cash lands in your bank account every night, you business legend. Number 3, in the past year, breweries have pulled in nearly 100,000 extra chatroom visits and raked in over $1 million in recurring revenue with apps of their own. Got the fib? Right, mate. Andrew reckoned this was a bugger idea, but joke's on him. I went and did it anyway. So book a demo today and let's show Andrew you're keen on packed tap rooms, steady revenue, and of course me, Willie, the Tapwise Owl. Cheers, Cobber. Now enough chin wag. Let's get on to the learny bit.
Hey, good morning, everybody. Dirk Loeffler here, SEKA Chemicals. First of all, thanks for CBP and Andrew to let me present here again. It's a great platform. I always enjoy being here. Been to CBP Connect Live and CBP Virtual, so it's an awesome platform. Thanks for having me again. Today, we're going to be talking a little bit about stainless steel and all the various destructive forces that can damage the equipment. So I've been doing cleaning and sanitizing in and out of breweries for almost 40 years now, and still see new things, different things. But over all these years, one thing that has always struck me a little bit is how devastating some of these things can be on stainless steel. Some have to do with chemicals, some have nothing to do with chemicals, but let's kind of dive a little bit into this, and hopefully this will help you to keep your equipment safe and protect your investment. Anyway, so we're going to talk a little bit about specifically 300 series stainless steel, since that's pretty much the only grade that we generally find in food and beverage plants. And when we walk into plants that have stainless steel inside it, we love to see it nice and shiny, and ideally with some atmospheric lighting like we have here. It all looks very beautiful. But if you pull the curtain behind, then oftentimes you find this kind of stuff. You find halogen corrosion, you find destroyed stainless steel from cavitation, rouging, chloride pitting again, and again more rouging. So various destructive forces that can kind of work on your stainless steel, and some are easy to remedy, some are very difficult to remedy. Some of them will literally leave your equipment destroyed. So let's see, kind of go with this. And a lot of brewers always look in their tanks and they're saying, hey, why does it look at this way? How did I get here? So let's try to look at this a little bit further and dive a little bit into the material of stainless steel. So to really talk intelligently about stainless steel, I think we need to kind of first cover some basics. What defines stainless steel, what defines the different grades, etc. So if we look at stainless steel basics, generally we define stainless steel as any alloy that has a minimum of 11% chromium by mass. We have different grades within that thing. We have carbon steels, we have other steels. So, carbon steels, we define those as our regular iron tanks. They really don't have any or very little chromium in them. Stainless steel has some very unique characteristics that makes it uniquely suitable for what we're trying to do with it with respect to food, with respect to cleaning and chemicals. One of the unique characteristics about specifically 300 series stainless steel is that because of the arrangement of chromium and other metals in this metal, it readily forms a passive film of chromium oxide. This is only like, if you look at the human hair, the chromium oxide layer is about 100 times less thin than a human hair. We're talking nanomillimeters. But it is a very powerful protective mechanism that protects the steel from environmental impact, also protects the product from taste impact from the various metals. So it prevents a layer from both sides of the stainless steel and gives it some very unique properties. Now, important to know is that this corrosion resistance or passive layer can be adversely affected. For example, if the steel is used continuously in non-oxygenated environments. Well, if you think about a brewery, these tanks spend a lot of time in a non-oxygen environment, namely CO2. Oxygen is kind of detrimental to our beer. The one thing that we're really adamant about is get as little oxygen into our beer as possible. That means we also have a lot of times very little oxygen in our tanks. And that is actually very detrimental to the passive layer. This passive layer prevents the tank from rusting, and when it says stainless, it doesn't mean stain none, it means literally stainless. So stainless steel still needs a little bit of TLC. It needs to certain treatments on an ongoing basis, but there's also quite a few things that can damage the stainless steel. Halogens, in particular, chlorides here, can easily penetrate this passive film and then allow corrosion to develop. So in this presentation, we're going to dive a little bit into all these mechanisms and see what's really going on. Also, just as a basic understanding, know that there's different grades of stainless steel. So there's the austenitic stainless steel, as we call it, which is generally the 300 series. What's unique about these metals is they are non-magnetic. That's the way the internal metal structure is arranged, that it just doesn't magnetic. So if you have a brewery tank and you have a magnet and the magnet attaches to the tank, generally indicates you have a problem. Martensitic steels, commonly like your kitchen knives, and so these are actually a little bit stronger, but they generally contain certain other metals that make it stronger, and they're also treated, and they have only a moderate corrosion resistance. So if you ever see your kitchen cutlery starting to corrode, then that's the reason why. We also have duplex steels. They're kind of in the middle of both, the best of both worlds, where we have some of the characteristics from austenitic and martensitic in one steel. These are partially magnetic. They have generally a higher strength than austenitic steels, which is generally not a big issue in beer applications, but in other applications, industrial, that can make a difference. They do have better stress corrosion cracking resistance. This can be definitely something that is important, and they're also a little bit easier to weld. So talked about the stainless steel, can it form a passive layer? Yes, technically all these steels can form a passive layer. The question is, what quality is this passive layer, and how much does it protect our steel? So if you look at this here, austenitic steels, provide an excellent environment to form a passive layer. We have a high chromium and nickel content that provides a very stable and self-healing oxide film. And if we add molybdenum, generally in 316, that can further improve resistance to chlorides. And then we also have the L grades, as we call them, low carbon, that will further increase the resistance against chlorides. You find those commonly in dairies. We call it dairy grade stainless steel, since dairies still use extensively bleach as a sanitizer, although they're also moving away now more to peracetic acid. Martensitic has a very limited ability to form a passive layer. Duplex steels, again, have a very good, not as good as 300 austenitic, but still very good. So for our purposes, generally, that is acceptable. Ferritic, just to make it complete here, have a good one. We generally don't find these tanks. So just for mention purposes, we're not going to get into those. This diagram just shows a little bit the different grades of austenitic stainless steels. You have this uploaded later online, so you can look at this a little bit further. What's maybe interesting to see on the right here, as we see the different percentages of the various chromium and nickel, you can see how the definition of the steel changes. And again, specifically as chromium and nickel goes up, we generally find our austenitic steels here, and that's what makes them so uniquely suitable for what we're trying to do. So for our purposes, again, today we're focusing, on authentic stainless steel 300 series. Generally, the brewery we find 304, 308, 316. Again, some of the characteristics, at least a maximum of 0.5% carbon, a minimum of 16% chromium, and enough nickel and manganese to retain the austenitic structure. That is the internal metal structure that also makes it non-magnetic. We have some what we call super austenitic stainless steels. We do sometimes find these for hot liquor tanks. We're going to talk a little bit about this later in the presentation, since they provide a much better resistance to stress corrosion cracking versus the 300 series, and that becomes an issue at elevated temperatures if you do have chlorides, in your environment. Again, we already touched on this quickly. We have the low carbon versions of austenitic stainless steel. Those have a maximum of 0.03 as opposed to 0.15% of carbon. And because of that, they become actually a lot more resistant against chloride pitting and corrosion. All right, so this covers the basics. Stainless steel, indestructible, maintenance-free. Well, think again. So just as Superman, who thought he was indestructible, has his kryptonite, our stainless steel has its kryptonite, as it turns out. Halogen pitting is probably the one that I see the most. I had an interesting discussion probably 4 or 5 weeks ago. I did a Master Brewers presentation here in Atlanta, and on a similar subject, and somebody came to me afterwards and asked me, in how many percent of customers or tanks do you see these problems? And to be quite honestly, I have to say that looking in tanks and having been doing so for 40 years, of that almost 35 years here in the United States, we do see these problems in, I would say, 98% of breweries here in the United States and about 95% of tanks. It is that commonly here. And in a little bit, we're going to get to the reason why we do this here extensively, whereas, for example, in Germany, I rarely come across this. But there's a reason for this. Poor quality steel and chlorides is always a bad mixture. This here is a once-in-a-lifetime pictures where a brewery had the genius idea to store their iodophore solution in a CIP tank for reuse. Well, it was a stainless steel tank, and if you know anything about halogens and iodophore, then you definitely know not to put this in a stainless steel tank. And yeah, this was the man wave from that tank, and the whole tank looked like this. So this tank was essentially destroyed and needed to be scrapped. We do find that pitting from chlorides is a lot more pronounced in acidic environments. So even lower amounts of chlorides in a highly acidic environment can produce pitting and halogen corrosion. So this year's, for example, in a brewery, again, in the Northeast, we do have elevated chloride levels in the water, where the brewery was using sulfuric acid on their brew house, but did not take the chlorides out of their water and ended up with chloride pitting on the manway cover from their brew kettle. Again, more pictures: chlorine dioxide, iodophore again. Got a million of them. Another interesting phenomena that we're going to talk about later is a phenomena called super concentrated droplets. This, for example, was caused by peracetic acid. So we get into this a little bit later here. Chloride pitting. So, if you apply chlorinated foam cleaners, for example, on the exterior of pipes and forget to rinse it, you end up with something like this. You see halogen hazing. So if you have something like this in your tank, this is most likely halogen hazing. RO water by itself, in ambient temperatures, not generally a big issue. However, if you use RO water and then don't treat it and use it in your hot liquor tank, then you're most likely to end up with something like this over time. RO water, because it is deprived of any and all salts, and water is a very reactive chemical. It wants and needs to react with things around it. And if there's nothing in it that it can be happy with, like salts, then it will literally go after your equipment and find something there to nag at. So that's kind of a summary. So if we look at destructive forces on stainless steel, and we look at the different mechanism and the different ways of doing this, we generally find corrosion from pitting, crevice corrosion, stress corrosion, cracking, general corrosion, and intergranular corrosion. Mechanical stresses and extreme temperatures can damage our stainless steel. One of the reasons why more and more companies go away from heat sterilization is that the extreme differences in temperature from heat sterilization to ambient rinses afterwards, etc., can put enormous stresses on welds and on metal and can cause failures or mechanical stress. We talked about chemicals like acids, hydrochloric acid, sulfuric acid at certain concentrations, at certain temperatures, will cause almost certain damage to the stainless steel. And we talked about the halide salts. We talked again chloride, bromium, those kind of things, iodine. Improper fabrication. We'll learn here in a little bit that improper welding can cause problems with the steel that will result in problems down the line. And then we also have, kind of rare, but I've come across it a few times, particle contamination from outside sources. For example, we were working with a company, they were installing a brew house outside, and then people were welding above the brew house. And as you know, when you weld, there's always the sparks flying around, which is actually small pieces of metal. They ended up on the stainless steel surfaces and then caused damage from there. So that is what we call particle contamination. Let's talk a little bit about each individual force by itself. Chemical attack, certain harsh chemicals. We talked about never use hydrochloric acid on your equipment. You really want to stay from sulfuric acid as much as possible. And again, we talked about the halide salts, chlorine, iodine, chlorine dioxide, all those things. They will and can destroy the passive protective layer, and then make the stainless steel very susceptible to corrosion. So some typical examples right here. Pitting corrosion. So here we're talking about generally a localized breakdown of the protective oxide layer, creating small localized pits. Generally that will look like this. This is kind of extreme ways, but you can have these little tiny ones here that are quite commonly observed, especially in manway covers, for example, where oftentimes the rinse doesn't get to. You get some spray there, but the rinse doesn't get to it. So, if you have a top manway cover, then those often we see this kind of corrosion. Crevice corrosion, I don't really see this that much, but when you have two pieces of stainless steel joined and there's a gap in between because you have uneven oxygen levels in there, we talked about that the oxygen is very important for maintaining the passive layer. It does promote corrosion. Generally this looks like this here. So this is, for example, a crevice corrosion that happened inside a improperly done weld. And here we see very typical for coastal regions where you have a lot of salt carried by the air from the ocean. This is a stainless steel bolt on a stainless steel plate, but then you see how between the bolt, the washer, and the stainless steel surface here, we see this typical crevice corrosion occurring. So very, very common, and something that definitely is a big ongoing issue for anybody that lives in coastal regions or on islands. Stress corrosion cracking, probably the most feared one of all. This generally will result in a destructive failure of the stainless steel, where the pitting and the tensile stress gets so bad that it will literally eventually cause a failure of the equipment. On the left side here, we see the mechanism, how this will work, and this is actually an ongoing kind of self-maintaining process that will just keep getting worse and worse as the pitting progresses. And this is a typical visible example. Sometimes the beginning stages you can't even see it, but you see how all the cracking here is happening Again, this will eventually lead to failure. So stress corrosion cracking. Generally in breweries, we find chloride stress corrosion cracking. In other industries like the oil industry, we have sulfide stress corrosion cracking. Don't really see this in breweries, but again, chlorides are very common, and we do observe this. Intergranular corrosion is kind of an interesting one. So this happens a lot of times if you see that in your equipment, the welds are starting to form like rust first, or you see failure of welds. This is most likely due to what we call an intergranular corrosion. So if you weld improperly on stainless steel, the excessive heat can cause the carbon to combine with the chromium, creating chromium carbide, which is not forming a passive layer anymore. So the chromium itself will form a passive layer, but the chromium carbide will not. So because you have these isolated areas generally, or potentially even larger surfaces of chromium carbides, you do see a lot of times corrosion occurring around welds. This can happen during improper heat treatment. Can also happen to impurities. So the reason why sanitary welders get paid a lot of money and literally travel around the country to do jobs is because it is a very difficult job and it takes a lot of skill to do it right. And again, it just even increasing the temperature by a little bit can cause essentially long-term problems for the entire stainless steel around the weld. This is how this kind of looks like. Typical different stages. This is probably how it starts. You see those along the welds generally. You see those rust marks. Then eventually, if it continues, you see that the weld will actually fail. Same thing here. This was under insulation and wasn't really caught until it finally started leaking. So a typical example for intergranular corrosion. General corrosion, we kind of see this very rare. I mean, if you're in a coastal area and you have stainless steel outside, you might see this over time. This is essentially where the entire surface gets attacked evenly and is leading to a broad, usually very destructive attack where the stainless steel will literally fail and large pieces will be failing and looking like the typical rust that we see from like iron normally. So this can look like this here or like this. Again, we generally see this in coastal areas, oil platforms, and those kind of things. Not too common in breweries, but just to mention it for the sake of completion. Particle transfer, we talked about this earlier, also something. So you got to be careful when you work above your tanks or your brew house, especially when you do welding or grinding. If these particles that could be just iron or metal or other metals other than stainless steel end up on your equipment, then that can definitely cause a significant damage to your equipment and then cause this particle transfer rust. Generally looks like this here. I've seen it. Again, it's not very common, but definitely something that can occur. Rouging is another one that I want to quickly talk about. I come across this more lately. It's kind of interesting. This didn't used to be as big of an issue as it is lately, but there seems to be a higher occurrence of rouging in equipment, and I think it is a combination of poor quality equipment in combination with sometimes chemicals that are not meeting the highest quality standards. So we do see, and rouging can vary, and there's actually 3 types of rouging. So let's go through each one here. Type 1 is generally something that happens somewhere else and just gets transported into your system. That's generally the one that can be easily fixed. Usually looks like reddish brown, flaky. It's generally an iron contamination or rust from an external source, carbon steel and piping or something. And it can generally be removed fairly easily with like a strong acid, CIP, or a repassivation cycle type of thing. Nitric acid, citric acid can take it off. Type 2 is a little bit more difficult. Now here we're actually talking about generally by the passive layer failing. We see this a lot with hot water application, steam, or deoxygenated water. So, this is something that is more severe, is more difficult to remove. Sometimes cannot be removed at all, at least not chemically. And generally here we're dealing with what we call magnetite. So it's a ferric oxide type of material that is also mixed with chromium or additional iron oxides. As a general rule, all rouging is iron oxide, just different types and different degrees. Type 3, the worst kind, unfortunately, black, blue-gray, thin and very adherent. Here, generally, what we have is poor quality stainless steel, high temperature applications. So we find this like in brew kettles, hot liquor tanks, and then in systems that haven't been properly passivated, or the owner didn't know that the equipment was such poor quality. Those are kind of we're looking at spinels here, and how does this look like? Well, this is the picture of a kettle. Sorry, this is a hot liquor tank, I believe. This is a bright beer tank, the bottom of a bright beer tank, and this is the typical sign of type 3 corrosion when it goes black. We call this a flash corrosion or type 3 rouging, when the entire stainless steel goes black. So again, generally all these things, have a failure of the passivation underlying, generally high chloride content in the water or coming in through certain chemicals, and actually oxygen. So if you use an oxidizer, for example, with your caustic, peroxide based, and your stainless steel is not passivated, and the stainless steel is bad quality. So a lot of things sometimes have to come together that would normally not affect a tank or a piece of equipment. But if all these factors come together, then you end with something like this. Again, we talked about the type 2. So pretty much every rouging can be fixed, but it takes different approaches. So type 1 generally can sometimes just be wiped off, because keep in mind, it didn't happen right there. It was actually carried in and just kind of deposited itself. So we can generally wipe, or, worst case scenario, run a passivation. In some cases, electropolishing, but generally passivation and wiping will take it off. Type 2 rouging, generally here we're looking at pickling. When I say pickling, low nitric acid, which we normally use for passivation here, would not be enough. You probably need to use a hydrofluoric nitric blend. Don't try this yourself. Hydrofluoric acid is a highly toxic chemical. Just to give you an example how toxic, a walnut-sized burn on your hand will kill you. So you really don't want to mess with this stuff on your own if you're not experienced and have the right safety equipment. This is an outside job for somebody with experience. Or another option would be to do electropolishing followed by a passivation. Type 3, again, this is probably the most difficult to remove. This one is almost, I must say, very hard to remove with chemicals. Extensive pickling might work, but you're literally taking now quite a bit of layer of your stainless steel. But it can be removed by either mechanical polishing or electropolishing. So that's definitely something possible. But yeah, generally you're looking at a very expensive way of refurbishing your tank, and definitely usually outside help. So when I talk about chemical corrosion, here's one thing that is very dear to my heart, and I think I'm the only guy in the United States who preaches this. It's kind of funny, but one famous of my many sayings I have: just because you can does not mean you should. In this case, rinsing your sanitizers, or more correctly, not rinsing your sanitizers. I talked earlier about why I don't find really this this destructive halogen pitting in tanks outside the United States, especially in Europe, because by law we are required to rinse every chemical out each and every single time. Well, by getting it out, we don't really have the problem of having to deal with these long-term chemical exposures. So let's take a better look at this. And I know everybody's screaming, is like, well, I need to, if I rinse my sanitizer, why do I even bother sanitizing? It's like, it is all possible. But let's talk about this. So the FDA really doesn't care about your equipment. The FDA only cares about human health. So, and the FDA says, okay, we let you do, sanitize your equipment without the requirement for a final potable rinse, as long as the residuals stay within certain limits set forth in the Food Chemical Codex. That means these are generally chemicals generally acknowledged as safe in residual amounts for human consumption. Iodophores, chlorine dioxide, pretty much any EPA registered product is approved, or the majority of them are approved, as not necessarily requiring a final rinse. But keep in mind, this is only from a health perspective. This is not from an equipment perspective. So if you think about it, if you sanitize your equipment and you let your chemicals sit there unrinsed, you're going to fill the tank up with beer, probably to about 80-90% of its volume, and then you leave some headspace for the krausen and the yeast. But the very top of your tank really will not see any liquid for the next 4, 5, 6 days if you're making ales, or up to 3 to 5 weeks if you make a lager beer. Okay, that is a long time for chemical to sit on stainless steel. And what will happen in the meantime, that if you use chlorine dioxide, if you use iodophores, if you use bleach, those chemicals will start to attack your stainless steel. And that's because generally chlorine dioxide breaks down into chlorides. Iodophore releases elemental iodine in the vapor phase, blah, blah, blah. So all these things will start causing to nip away at your tank. And then we find ourselves, we have no pitting here, but we have pitting in the headspace. That's because this was above the water surface. So, then in addition, the CO2 atmosphere and the lack of oxygen, further, makes our passive layer weak. So now we have a halogen, a weak passive layer, and almost ideal conditions for the halogens to break down the passive layer and start going after our stainless steel. I generally discourage the use of halogen as sanitizers in the first place. And I know when I first came here in the early 90s, iodophore was everywhere. I mean, everybody was using iodophore as their primary sanitizer. And then it went more and more away into peracetic acid. But still today, I come into breweries that use iodophore, use chlorine dioxide as their primary sanitizer, and do not rinse. These are products that cannot be used without a final rinse on stainless steel, period. There is no if or but. You will damage your equipment, you will get pitting, you will damage your stainless steel. There is no if, there's only a when. So be aware that if you use chlorine dioxide, if you use iodophore, if you use bleach, any of those things, it will pit your tank. This, for example, brand new tank, 1,000 barrels, never been used. Commissioning, the dosing pump malfunction, put a huge slug of iodophore in there, and this is what it ended up. It literally just destroyed the inside of the entire tank. So it just takes one application for this to happen. Chlorine dioxide is another one that is kind of, and I'm going to quickly jump ahead here. Yeah. So that I want to kind of talk about is the majority of breweries in the United States use what we call the acidified or the activated chlorine dioxide as a sanitizer if they use chlorine dioxide. Now, keep in mind, if you use sodium chloride as your primary sanitizer, the activation rate is very, very low. leaving you with a very large amount of unreacted sodium chloride in a very acidic environment. Okay, so the result is this one here, and I've kind of broken this down a little bit for you guys. So sodium chloride is mixed with citric or phosphoric acid. It produces acidified sodium chloride, and this reaction generates chlorous acid, which then forms chlorine dioxide, because chlorous acid is unstable and it actually decomposes into chlorine dioxide. So this is kind of the chemical reaction. This is why you have to put it in the container and wait for a little while before you actually have chlorine dioxide, because it first reacts into chlorous acid and then into chlorine dioxide. Now, the problem with this reaction is that, again, the activation rate is 5 to maximum 35%, with the remaining portion being chloride ions. And again, the more acidic conditions favor higher concentration of chlorous acid. The problem is, when you do this in acidic conditions, you also end up with hydrochloric acid in the breakdown process. So, which is, again, not good on stainless steel. So if you leave this sitting in your equipment, not a good idea. So this is a big no-no. Do not use chlorine dioxide as a no-rinse sanitizer ever on stainless steel, because you will pit your equipment. There is no if or but, there's only yes. Now, there are ways to produce almost 99.9% pure chlorine dioxide, which is better, because you don't have all the chloride attacks breaking down your passive layer. But even those things will break down into chlorides afterwards, because chlorine dioxide is also not a very stable chemical. So while you're taking out of the equation the majority of the chloride, of the residual chloride ions, you do have the chlorides that produce from the chlorine dioxide itself. So those are available. We actually carry those, but just use peracetic acid. It's cheaper. It is just as effective. And it's not nearly as dangerous, and it's not nearly as dangerous on your stainless steel. So halide ions and passive layer disruption in general, just to kind of understand the process. We talked about this. So stainless steel relies on a thin passive layer. Talked about that one. This layer is compromised. Now we can get in there and start attacking it, and this is how this actually looks like in a kind of a form. So here we've broken our passive layer. Here's our passive layer. The passive layer has broken open by chlorides. Again, can start at local imperfections or breaks. Now this becomes an area where pitting corrosion can take place. Chlorides get in there. Chlorides react with the iron and the water. Here we have our HCl already, ready to form. And again, keep in mind, this is much more pronounced at higher temperatures and or lower pH levels. So, and this is why we generally see this a lot more common in acid CIPs or hot liquor tanks. Kind of break this down a little bit further. Again, we're kind of flying through this because of time, but you see here the chloride ions penetrate metal chloride formation, hydrolysis creates our hydrochloric acid. Because we now have hydrochloric acid in the pit, the pit keeps getting deeper and deeper and worse and worse. Now we have our pit propagation. And again, this is what we call an autocatalytic process. That means it'll just keep regenerating itself into more chlorides, and then the whole process starts over. So this is just going to get worse and worse and worse, and it's an ongoing process. The HCl formation, we know that hydrochloric acid is not great for stainless steel ever. But we do see here how temperature can affect that formation and the effects on the stainless steel. Again, hot liquor tanks are the most prone. Brew kettles can be very prone to this one. So just be aware of this. Another demonstration or illustration of how this works is it's really an electromechanical process. So we have the metal surface was built, which presents a large cathode. And we have our little pit here, which creates a small micro anode. So inside the pit in our anode, this chemical reaction takes place, which again, amongst other things, produces always a little bit of hydrochloric acid. So we have an acidic chloride-rich environment, which unfortunately further promotes the metal dissolution. That means this pit's going to get deeper, and this process is going to get more and more pronounced, and it's going to just keep breaking down our stainless steel. And on the outside, we have this reaction, which ironically creates an alkaline, low oxygen environment, which then further breaks down the passive layer and prevents the passive layer from reacting. So it's kind of the worst of all scenarios. Just kind of how chlorides can be affecting our pipes. So this was actually a company, a brewery in the Northeast. After an extended shutdown, they brought in a contractor and had all their pipes cleaned with a chlorinated alkaline foam cleaner. Well, the contractor unfortunately forgot to rinse the pipes down, and destroying about $300,000 worth of process piping in the process. They had to essentially rip all this piping out, do all the piping over before they could start up again, adding another extensive bill to their already extensive shutdown bill. Want to quickly talk about the super concentrated droplets. So this is a phenomena I came across the first time at a large brewery in California, and we were actually just doing an audit, looking at tanks, and we opened up the tanks, and we observed this drop running down the side of the tank, and we noticed as this drop was running down the side of the tank, it was creating a pitting in the tank surface. So we did some more research on this, and it turned out that we were actually dealing with a phenomena that is called a super concentrated droplet. So again, if we don't rinse our chemical, in this case peracetic acid, we started with 150 parts per million. It was at the top of a tank. The tank hadn't been used in a while, and the PAA was just sitting there. Well, the problem is PAA is not just PAA. You're looking at several different chemicals that coexist in an equilibrium, and they evaporate at different ratios. Unfortunately, it seemed in this case the water evaporated first, leaving us with a very, very high concentrated peracetic acid solution. And at those high concentrations, peracetic acid, does become corrosive on stainless steel. So what used to be 150 parts per million probably became easily, 100,000 parts per million or even more. And then you end up with these super concentrated droplets corrosion. So just another thing to know about, that this can happen, and another reason why you do want to rinse. Just to talk about that, water can often be the cause all by itself. Water can carry, depending on where you're located, a lot of chlorides in it. It can be iron, there can be a bunch of things. Keep in mind too, even if you do a carbon filtration of your water, it will break down the free chlorine in your water, but it will not take out the chlorides. Chlorine breaks down into chlorides, which is an elemental ion, and it will remain in the water. And the tolerance for chlorides of 304 and 316 is reduced by decrease in oxygen. So if you have a CO2 environment like in your tanks, lower pH values, acid CIPs, and high temperatures, brew house, hot liquor tank, etc., etc. So again, RO water by itself can cause problems. So I would say if you have an RO water and you need to put it in a hot liquor tank, see if there's one salt that's present in all your formulations and add that to it to keep the water something to be happy with, so it doesn't go after your stainless steel. We talk about why wells fail first. The intergranular corrosion, the heat creates again the chromium carbonate, the carbon chromate, and that will cause a very weak and we call it sensitizing layer. It is no longer able to produce a passive layer like the rest of the stainless steel, and then the passive layer breaks down and causes problems. Again, we have first chromium carbide precipitation in what we call the heat affected zone. The grain grows, and we also have what's called a sigma phase formation. You guys can go through this. I'm kind of flying through this because I'm almost out of time. So how to avoid damage to equipment? Know what's in your water. Rinse your sanitizers. If you want to ask me how to do it safely and still be able to have some sanitizers in there, avoid the use of halogens. Some resources here that'll be posted on there. And again, if you have any questions, I'm always available for you via email or via telephone. This is our main number here. If you go on our website, you also find my contact information. Or hopefully this was informative and taught you a little bit about stainless steel. And again, if you have any more questions, contact me directly, and I'll be happy to work with you. Thanks again for CBP for letting me presenting here today. And I think I've made it just in time in my 45 minutes here. with 10 seconds to spare. So the remainder of the presentation was a little fast, but then again, if you have questions, my contact information is here. Definitely contact me. Cheers, enjoy the rest of the presentation.
Thanks for watching. If you enjoyed this session, we'd love to see you in real life. We host in-person workshops across the country for craft beer professionals just like you that are held in some of the most exciting beer destinations around. These immersive events are designed to help you grow and connect with others. You'll meet peers from across the country and leave with actionable strategies for success. Connection has never been more important, and you can learn more at cbpconnects.com. Cheers. See you there.